Okay, so today we're going to be sort of branching out from what we did last time, where we had discussion on the symmetry elements and operations, and we're going to be using those to assign the character table or assign the point group symmetry. And this will be quite a bit of review for anybody that's had symmetry in the past and going through the flow chart and doing the character table. So it's always nice, I think, to have some review. It makes you feel comfortable with the material and so on, but we'll do some of the more challenging molecules that they have on SymOtter. You know, and maybe in the undergraduate we had the simple molecules. We'll do some of the more difficult ones, and maybe even get into some of the inorganic molecules for those folks that are doing inorganic research. And so what do we mean by point groups? Well, it's this groups of symmetry operations of a molecule. And the center of mass is that point that's unmoved by all these symmetry operations. And so it's the point in the term point group. There's a different section of symmetry that we use in inorganic in particular, but also some organic researchers use it, and that's called space group symmetry. So when you get into crystals, the points move into space. And so you have translations and dislocations and translation reflection operators and all kinds of other operators that we don't have in point group symmetry. Okay, and so you would have a translation reflection, or maybe translation rotation, and those would be space group operations. But the reason we're talking about point groups is that's separate from space groups. And so when you get into inorganic and crystallographic studies, then you get into the space group symmetry. We use this Schoenflies notation. So I give you these official terms because those are the things that I'm going to be using. So make sure that you understand the terms. The Schoenflies notation is what we're using when we talk about C3V, C2V, tetrahedral, or TD, octahedral. And so that's the type of notation that we're using. We're going to practice in a little bit using this SymOtter page. So the goal is to get to one of these endpoints and to define or describe or identify the point group for a particular molecule. And so in order to get to those endpoints, they've made this flow diagram. It shows up in several different texts, and they use one on the SymOtter webpage. And it has a series of questions. And so these diamonds are question boxes. You have a yes or no question, and then it tells you how to go through the diagram. And so it's a flow chart. And so like in this case, let's just take CO2 here. You come in, the question is, it's linear. Yes, it's linear. You move over here, does it have an inversion center? Yes, it has an inversion center, therefore it's d infinity h. And so all of the linear molecules that have the same atoms and the same pattern on either end are d infinity h. If it's linear and it does not have an inversion center, then it's C infinity V. So all linear molecules are one or the other. It's two different categories. Okay. If it's not linear, then you get into these more complicated questions. Like, does it have two or more unique C3 axes? And so it's looking for high symmetry molecules. And so in this case, like in methane, you've got a C3 axis coming out here. You've got a C3 axis going down. So every CH bond is a C3 axis. And so it's got 4 unique C3 axes. And so you would say yes to that. Then you get to an inversion center. Does it have an inversion center? No, because this hydrogen here has no hydrogen on the bottom to invert into. So there has to be, across the center of mass, has to be the same atom type on the other side. And so you would say no for methane, and that would just a no, yes, and a no gets you to tetrahedral. And anything that looks like methane or has the same kind of structure as methane, like carbon tetrafluoride, again, 4 identical species on carbon, it's going to be tetrahedral. Let's say it does have an inversion center, then you get to 5-fold symmetry versus 4-fold symmetry. If it has 5-fold symmetry, it's going to be an icosahedron. So that's icosahedral point group. You see the five-fold axis here. All of these points here have a five-fold axis. Now, if you expand this icosahedron out and you take all of those five-membered rings and you move them sort of out in space and you fill in the gaps around those five-membered rings with hexagons, then you have the soccer ball or the buckyball, C60. So C60 is also an example of an icosahedral molecule. So next time you have a traditionally patterned soccer ball and you look at it, the black pentagons are the five-fold symmetry species here, and they're surrounded by hexagons, and that's that C60. There's 60 vertices on there. Get you a Sharpie and mark them. Count them up. You have all 60 vertices on that, and all of them are three, vertices that can have three connections. And what's interesting about that is even though they're strained, every carbon is a strained sp2, because every angle in that ball is roughly 120 degrees. And so you could look at that, and they're all sp2 carbons. And that was really sad because there was a professor, Ken Hedberg at Oregon State University. So Rick Smalley at Rice saw the mass spectrum of soot. And it was just, again, you could think about the mass spectrum of soot and how you would have all the different mass to charge ratios, right? Because it's such a complicated substance. It's the combustion products, solid combustion products. And so pretty much every M over Z had some signal, right? So this is, I'll just go ahead and draw it in here just because it's an interesting story. Okay, so we had soot, mass spectrum, right, M over Z, and number of ions. And it looked like this, right? Every M over Z had some ions, but what Rick Smalley saw was these really narrow peaks that were in there. So it looked like just a mass of signal, but a bunch of little narrow peaks. And he zoomed in on those and thought, why, statistically, would there be any variation? Why isn't it just a smooth continuum? But there were individual peaks on there. And he started looking at the numbers of those mass to charge ratios. And they were like C60, C70, C356 or something. And he started looking at those numbers, and they started ringing a bell. And he started looking at the vertices on these Buckminster-Fuller geodesic domes, how to make these dome structures and the number of vertices that you had. And these were magic numbers of carbons that would make like a spherical and oblong shell type molecules. And so he and I think his Bob Curl was another professor at Rice and a professor in Japan who analyzed the numbers and came up with these allotropes of carbon as a hypothesis. And they got the Nobel Prize for it. But theirs was just looking at the magic numbers associated with these peaks in the soot. And my buddy Ken Hedberg, or Professor Ken Hedberg, buddy, that's funny, really personable guy. He did the electron diffraction on C60 and showed that there was all one type of carbon. He showed that they were all sp2 carbons. Essentially, there was one bond length in C60. He had this really complicated molecule with one bond length. Okay, and in my opinion, because he verified that it was one type of carbon in that molecule C60, should have shared the Nobel Prize, because they just worked it out that there was the right number of atoms for these geodesic dome structures, but the experimental data that showed they were all the same type of carbon was done at Oregon State by Ken Hedberg.
So why the Nobel Prize?
Oh, why? Just in general, the Buckminster fullerenes? Okay, this was actually legit because at that point there were only two types of naturally occurring carbon. There was graphite and diamond. Okay. And so they discovered a totally new naturally occurring type of carbon. Gotcha. So those Buckminster fullerenes are a naturally occurring type of pure carbon. And so it would be like oxygen is O2, right? And like if you discovered ozone, which maybe, you could argue is a naturally occurring form of, but it's also an excited type of, but it's reactive. But like if you discovered ozone as O3 and it's naturally occurring, that's a whole nother naturally occurring form of oxygen. And so that was what made it Nobel Prize winner. But it's a great question. Pardon? Yeah, so any combustion, like if you get soot out of your fireplace chimney, it will contain very small amounts of C60 and C70. And so they figured out a way to synthesize it in higher yields at Rice. And so we started in my undergraduate days, this was when this was going on, we would buy some from them, but it was $200 a gram. Yeah, so they were making soot and charging $200 a gram. It was purified soot, yeah. Yeah, anyway, it's kind of fun. So that icosahedral, we kind of went down a long rabbit trail for that, but that's that C60 is an icosahedron, and it looks like a soccer ball, and you can look at a soccer ball and see all 60 vertices. Then we get into these lower levels. We have the highly symmetric over here, the very low symmetry groups here, and then the intermediates in the middle. Okay, let's start with something with no symmetry. If we say no on the whole flow chart, and it doesn't have any rotational symmetry, no reflection symmetry, no inversion symmetry, we have C1. And that 1 indicates just the E identity. Okay, and so most of nature is C1, to be honest, right? But we have local symmetry. So like even in the hemoglobin protein, this enormous thing is the C1. But if you zoom in on the iron and put it inside the porphyrin ring, it might have, say, a square planar or octahedral symmetry. So the local symmetry is still incredibly important, even in a larger C1 molecule. Okay. So let's go through the flow chart on SymOtter, and we'll look at all of these different types of molecules. Now, let's go. Before we do that, though, let's look again to see the usefulness of this. We did the even and odd description of our particle in a one-dimensional box wave function. Can we assign a point group to our one-dimensional box? And you can. So we can come along and say that the ground state is even because you've got these points here that are the same sign on either side of the x-axis. And remember our inversion operator, I was equal to -1, -1, -1. This is from last time. Okay. And that in one dimension, we just have I is equal to -1. Okay. And so what we have here is the inversion operation. If we go from x to -x, we've inverted it. Okay. And the point group that has only one operation other than E is CI. And so CI has E and inversion. And so this is I think the most appropriate point group to use for our particle in a one-dimensional box. And so this now allows us to use these Millikan symmetry notations here to label our wave functions. Instead of just labeling our wave functions even and odd, we can now label them with these rows in the point group character table. And so the top row is even and the bottom row is odd in this particular one. And so we can label these wave functions. So the ground state wave function is AG. The first excited state was odd, and so it's AU. And then the third wave function is AG, and so it alternates going up and down. And this is one of the uses of point group symmetry and group theory, is our ability to label the energy levels. We see this in inorganic. We see this in a lot of other fields. And we did this on a Post-it note last time, only now, instead of doing even and odd, we would label them with their Millikan symmetry notations. And so let's do this one. So n equals 1 was Ag, and n equals 3 was Ag. And so we need to look at this and see what light is. Light is odd, but let's go back to our character table. And we can look here. If we have X polarized light, the character table tells us what the Millikan notation is for that. So we can use that character table not just for our wave functions, but also the interactions with nature, like light or rotation. So here's the rotation around X or Y or Z. And so we're going to put in AU for X polarized light. So right here in the middle, we have AU. And so then we multiply these together. A times A gives us A. And then we use the GU multiplication rules. If we have even times odd, that's odd, so it would be U. And so here we have, again, A times A gives A, and G times U gives U. So that's an odd function. So the integral over all space of an odd function is equal to 0.
This one, the homework quiz, that's what we're figuring out. Right?
Mm-hmm. And so I'm going to say get used to this. This is what we're going to be doing quite a bit, is identifying what energy levels are labeled with various symmetries and using light and determining whether this is an allowed transition or a forbidden transition.
So do they always operate AG, then AU, AG, and AU all the way up with energy levels?
Yes. Mm-hmm.
So we
once you establish that pattern, then it just continues up.
Yeah.
Mm-hmm.
It explains the selection rules.
Yeah. And so we could look at that and we could generalize it. We could say, well, we will always, let's just go ahead and do this one. This one is AG, 4 is AU, light is AU. A times A gives A, and U times G gives U. And then we have this U come down. And we look at those. A times A gives A, U times U gives G. So the integral over all space, that's what that bracket means. Remember, Dirac notation, that's the integral over all space of an even function. And so that's not equal to 0. That's the downside of this, is that we can't determine that it's 8.3, but we can determine that it's not 0. So it's an allowed transition. Now look at this. Once we look at the symmetries, we can get out of individual quantum numbers and we can look at the symmetries. And so we can say any UG levels can be connected by light. And so we can use that pattern to say this is a G to U transition, and so that's okay. And this one here, from 1 all the way up to 4, is a G to U transition, so that one's okay. This one, 2 to 3, that's U to G, that's okay. So we can come up with the selection rules here just from symmetry. So we can say delta N is equal to plus or minus 1, plus or minus 3, plus or minus 5, etc. So that's the symmetry way to determine those selection rules, which is much faster. In using the Millikan notation, we have to know the character table. And to get the character table, we have to know the point group. So we're going to expand on the character table more next time, but I just wanted to show you sort of the point. So what we do is, here's the character table, and then here's the direct product table. We were just figuring it out up here, but you can go and look at the direct products and see these multiplications down here. We'll get more experience with that in the future. Okay, so this point group is what we're looking at now. that we're going to be emphasizing. So we'll talk about the character tables more, but the point is, when we do these symmetries, the top row is the only even row. And so once we finish doing all these multiplications, if it's the integral over all space of any function that's not the top row, then it's 0. So only if it contains the top row will it be a non-zero integral. So let's focus now on this point group, this Schoenflies notation. So we're going to practice with the SymOtter website. And then we'll pick up the character table stuff next time. Let's see, let's do display capture. Yeah, okay, that'll work. Okay. Yeah, we got it. So last time we did a little bit of the tutorial on the symmetry elements, and so now let's do the symmetry challenge. So we'll pick a simple molecule first. Let's do allene. It's not that simple, but it's somewhat simple. So here's allene, C3H4. Okay. So the first question in the flowchart, does it have an infinite rotation axis? It's another way to ask, is it linear? No, it's got a C2 axis, but it doesn't have a C infinity axis. So we're going to say no. Does this molecule contain 2 or more unique C3s? It doesn't have any threefold symmetry at all. Right? It's got 3 carbons, but it's not a rotational, axis that would rotate those 3 carbons. So there's no threefold symmetry at all. So we would say no. And if you say, wait a second, do that question again or explain it, please raise your hand. Okay, it's not a risk. Okay, so then it says, find the highest order proper rotation axis if any are present. So does it have any rotation symmetry? We're looking here at a C2 axis. Do you see that?
Yeah.
Why is it not a C4 axis?
Because they're not the same on.
Yeah, so if we rotated it 90 degrees, it would move over here, but there's no hydrogen there. It has an S4 axis, okay, but not a C4. So we're going to pick a C2. What?
My students are about mid-class. So.
Oh, okay. I was like, S4. Oh, my gosh. Yeah, so, okay, so we picked the highest order. So this we're going to call this the C2 axis right here. Does it have 2 C2 axes perpendicular to this? So let's look this way, kind of diagonally on this molecule, right here. It would go, all of the C2 axes go through the center of mass, so it has to be through that center carbon. And it's got to be perpendicular to the one that we identified. But look at this hydrogen in front. This one can rotate around to this hydrogen in front, and the hydrogen in back can rotate around to the hydrogen in back. And the carbons can rotate into the carbons. Do you see the C2 axis? And then if I go 90 degrees to that, there's another one. Do you see it?
I see it now. I couldn't see it on my own.
Yeah. Okay, so we're going to say yes, it has 2 perpendicular C2s. Then does it contain a horizontal reflection plane? So if we pick this vertical axis as the principal symmetry axis, is there a reflection plane that's 90 degrees to that? And I would say no, because this hydrogen is coming out of the board, and if it comes down here, there's not one out of the board. There's one behind the board, but it doesn't have anything below it to reflect into. You can see it if I look down. Like, see, there's no hydrogen below that it can reflect into. Okay, so we're going to say no to that. Does it contain 2 dihedral reflection planes? Those contain the principal symmetry axis, and so there's a reflection plane here like this, right, that reflects those back hydrogens into each other, and there's a reflection plane like this that reflects the top hydrogens into each other. You see the reflection planes? So we'll say yes to that. You have determined the point group to be this D2D point group. So let's check our answers. If we check answers, it says, they're all green because we got them correct, okay? But look here, we can get to this, and it says select the highest order rotation axis. So show it. Well, we got it right. That was the C2, okay? We could hit play, and it will rotate it. So you check your answers and see like if you were seeing it correctly. Let's come down here and pick these vertical or these 90-degree or perpendicular C2s. We found those. We're going to hit play. That's that one. Okay, let's rotate around to that one. So if we hit play. Yeah.
So that is tricky.
Yeah.
Because they're like off equal.
Yeah, that's right. So if we look down from the top, look at them. They're 45 degrees off. Okay. So let me play those. See, there's that one, and then there's that one. And they're perpendicular to the first one. Okay. And then we come down here. We can show the dihedral reflection planes, and we can play those. That's the top reflection, and that's the bottom reflection. Yeah. Okay, so if we look at it from the side, and the carbons don't move because they're on the axis. They're reflecting too, but they're on the axis. So that's a D2D molecule, allene. Classic example of a D2D. Let's pick one that's crazy. Well, let's pick one. Let's do this one. Bromochlorofluoromethane. Okay. Is it C infinity? No, it's not linear. Okay. C3 axes? No. Any proper rotation axis? No, no rotation. So we're going to say none. Okay. Does it contain a reflection plane? No. Contain an inversion center? No. You have determined this to be C1. Okay, nothing to show here, just, yeah, nose all the way down. BR5. No, BRF5. So that's a bromine in the middle and 5 fluorines. Okay, let's, without using the flow chart, go ahead and write this down. Like, try to write down the point group for this one. Looking at it.
This is Y5.
Say again?
What's the molecule again?
It's BRF5. So I guess bromine pentafluoride. And if you do the Lewis dot structure, you're going to have extra electrons on that bromine, and they're going to go on the central atom. And so that's why that sixth position is empty. There's lone pairs at the top. Okay. Yeah. Okay. It's not linear, right? So see if you got it right. Did everybody write their point group down? What you think it is? No cheating in the back there. Everybody shout out their guess on the count of 3, okay? Everybody at the same time, so you're not listening to someone else, okay? Then you got to speak loud. A lot of folks don't speak loud, okay? So on the count of 3, say what you're going to say. I'll say 1, 2, 3, and then you say it. 1, 2, 3, and then you say it. Okay, 1, 2, 3.
C4V.
Yeah, C4V. Very good, very good. All right. So at C4, you got that right there. Yeah. And it's V because the vertical reflection planes, but the H would have to have a horizontal plane. So there has to be top and bottom have to be the same. So like C3V, C4V, C5V, C2V, the left and right look the same, the front and back look the same. You have all those vertical reflection planes, but the top looks different than the bottom. So that's the clue. It's got fourfold symmetry, but the top looks different than the bottom.
But isn't it also different whenever you assign your highest degree of rotation? So say, for example, you look at it as side view, and you do the same argument, just curious.
Yeah, but when I say top, typically that highest fold rotation will be the z-axis, and so I set it up to where that's the z-axis, and the z-axis is going up, and so the top looks different than the bottom. But around the molecule, you have lots of reflection planes. If it's C4V, you have 4 reflection planes. Okay, gotcha. Yeah, and so we'll go through this real quick. No on this infinity, no on the threefold axis. We'll pick the C4 axis. Okay, and select that. So that's going up and down. Are there 4 C2 axes perpendicular? No, because the top looks different than the bottom. So we can't do a C2 axis perpendicular to that. Okay, so we say no to that. That gets us out of the D groups. That puts us in the C groups. So we know it's a C something. And since it has 4-fold symmetry, it's going to be a C4. So does it contain a horizontal reflection plane? Again, the top would have to look like the bottom for that. So we say no. And then does it contain 4 vertical planes? And it does. So let me stop the spinning. Okay. So that's a vertical plane, left and right. Okay. And obviously the other bond is going to be one of those. But we can't choose another bond because we've already chosen this one. It's the back side of that other reflection plane. So it's this middle one. This is a dihedral reflection plane. It doesn't contain any bonds. And this is another dihedral. So we have 2 dihedrals and 2 sigma V's and sigma D's. But there's 4 of them basically. And so we say yes. And so you've determined it to be C4V. Okay. We can show some of those. Here's those planes. Here we can play them. So that's a sigma V. It's supposed to do all 4 of them. That's a sigma V. That's a, okay, it's not doing the sigma D's. Oh well. Okay, let's do some inorganic compounds. Yeah, let's do this one. This was the... So here's an octahedral complex, right? Sorta, right? But we've got 3 and 3, and there's a couple of different ways to put 3 things on an octahedral complex, right? We could put all 3 of them on a face, because remember, octahedron is 8 faces, so 8 triangular faces. There's 6 components, but it makes 8 faces. And so a triangular face is what we're talking about here, and that's what FAC means. FAC means facial. Or we could do meridional, around the meridian. Okay? So you could put 3 things on an octahedral complex this way, where they kind of go around one of the equator or from the pole down. Or you can put them all on a face. Oops, on a face like this. And they're going to be different point groups, which means they're going to have different energy levels, which means they're going to have different spectra because they're going to have different selection rules. And so we could use spectroscopy to tell the difference between these 2 things because of the selection rules. So that's why the symmetry, again, the symmetry is important and able to determine the molecular structure. We get different spectra from a facial or a meridional octahedral complex with 3 and 3. So let's go ahead and do this one.
Now, if it was 2 and 4, equatorial all 4 of the ones getting on the...
Yeah, so it could be, 2 on the poles and 4 around the middle, okay? Or we could do 2 adjacent to each other, and you get 2 different point groups that way, too.
What does that mean? What's the term for that one? Is that axial or...?
I would say equatorial or axial. So if the 2 were on the poles, that would be axial. And then if the 2 were beside each other, I would call that equatorial. So you have the poles are the same as 2 of the equator, and then you just have 2 others on the equator. So that would be a way I would name it. I don't know. Oh no, cis and trans. They did cis and trans that way. So it would be. So that's the cis one, and then this is trans. So they're opposite of each other. Okay, so cis and trans is what they use. Yeah. So.
In our homework, we have equatorial and axial.
Okay, so yeah, so I'm sorry about that. I made that up, I guess. Should have been cis and trans.
So cis and trans.
Yeah.
So trans would be equatorial, or it would be axial?
Axial would be trans, yeah. Yep. Thanks for asking that. So here's the FAC. Can you guys look at that? Let's just talk it through. On the count of three, what kind of point group do you think this is? So look at it. Yeah, I'll rotate it, toggle the spin. So it's not exactly perfectly lined up. Okay, so get in your mind what you think it is, and I'll count to three and you say it out loud, okay? 1, 2, 3.
C3H.
Okay, I heard C3H and I heard a C3V, and I didn't hear anything from about 10 people.
I didn't know whether it was H or V.
Yeah, and once again, so I've kind of lined it up where I see threefold symmetry. You see that? You see a C3 axis. So let's put that C3 axis up and down. Let's get away from the traditional drawing of an octahedral complex, and let's set this down to where the threefold faces on the bottom or on the top. So to make that your C-fold, and so the top looks different than the bottom. So that eliminates the H. Yeah. See what I mean?
Yeah.
Yeah.
Yeah. No, I got
the bottom and the left looks like
Yeah. So if you get it to where if you identify a principal symmetry axis and go ahead in your mind and stick that up and down as a z-axis, then the H would have to be horizontal. And that's why I want to get that vertical, because that's what H means, is horizontal axis. So let's put that z-axis as our principal symmetry axis up and down, and then a horizontal plane by definition will be horizontal.
So it's like as a jack sits on a table.
Yes, this is like a jack with three of the points painted differently than another 3 points. Okay, and so we'll go ahead and do this. Does it have an infinity axis? No. And it's not two or more unique C3 axes. It's got one C3 axis. Pick 3, select. Are there C2s perpendicular to that? No, because the greens and the carbonyls down below are not going to match. So we're definitely in a C group, and it's not a horizontal plane because the top and the bottom look different. And so then, does it have 3 vertical planes? Stop the spin. So we're talking about vertical planes. So here's one right here, a mirror plane, splitting the screen left and right look the same. Okay, and if you've got one of those and it's threefold symmetry, you've got 3. Yeah, because you just rotate it again and rotate it again, and you've got all 3 of them. So we say yes to that. And we've got C3V. Yeah. So this is a really great website for learning symmetry and identifying point groups. What is neopentane? Oh, that's cool. Who knew Neo had his own molecule? That's a joke, by the way. Yes, Matrix fans?
Yeah.
Yeah. Okay, just in general, I mean, again, this is a kind of a complicated molecule, but if you're just looking at it, what do you think it is? It looks tetrahedral to me. I mean, look at that central carbon. None of these other methyl groups really break that threefold symmetry around the central carbon, and I think that's the key. The tetrahedral group is governed by that threefold symmetry, and if you don't put something on here that breaks it, it's still tetrahedral. Okay? So that's a C3 axis, that's a C3 axis, that's a C3 axis. So every carbon-carbon bond is a C3 axis. It's not a C infinity, so we'll say no to that. Does it contain 2 or more unique C3 axes? Yes, it does.
That's 4.
Yeah. And then does it have a C5 anywhere? There's no 5 anything in this molecule, so we'll say no. So does it have 2 or more unique C4 axes? No. This is not a C4 axis. This is a C2 axis. It's an S4, but not a C4. Okay. And so we'd say no to that. Does it contain 1 or more reflection planes? Oh yeah, for sure. Like this carbon-carbon-carbon angle here, that's a reflection plane. And there's one this way. And so it's definitely got 1 or more, so we'll say yes. Does it contain an inversion center? So I'm going to draw it this way. Look at this carbon here. If it inverts through the center of mass, there's no carbon there for it to invert into. So no inversion center. So we'd say no. We determined it to be tetrahedral. So you've eliminated icosahedral and all of those others and got to tetrahedral. But your normal intuition, if you look at that molecule and you say, well, I kind of think it's tetrahedral, it's good to do a check to make sure the threefold symmetry is not broken. And if it's not broken, it's tetrahedral. Okay. Do you want to do the cis one? Let's do the cis one here. All right, this one you should be able to do quickly. I want to do it a little off axis like that, okay? So get your answer in your head, okay? And I'll count to 3, and everybody participate, okay? 1, 2, 3.
CGV.
Yeah, and I heard a bunch of C's, and then it got quieter. 2, so then a smaller V. But you got it right. It's just like water.
CGV.
If you see this, it looks like water, right? Because it has a oxygen, 2 hydrogens. It has something in the middle and 2 on the left and right side look the same. The front and back look the same, but the top and the bottom are different. Okay, so it has those 2 reflection planes and a C2 axis, and that's C2V. Okay, so that's the fastest way to do some of these. If you can have classic molecules and you say this looks like water, therefore it's C2V. Okay, let's do one that looks like, what is methane? I mean, what is ammonia? What's the point group for ammonia? C3V, okay? And so then let's, oh, they don't have acetonitrile in here. Shame on them. Okay. I was hoping to find acetonitrile because it looks like ammonia, but with a hat. Okay, let's look at this one. Okay, look at this one. You know that ammonia is C3V. And this bottom piece looks like ammonia. Does putting an atom on top of ammonia change the threefold symmetry? Does it add an inversion center or anything else? It doesn't change the symmetry at all. So if you know ammonia is C3V, and then you find this molecule, you will say, oh, it looks just like ammonia. By symmetry, it looks just like ammonia.
Now, if that was the same as the other things on it, it would be a tetrahedral. Right? So
Yes. If this was another hydrogen, then now it looks like a methane. Yeah. And so you would associate it with a different type of molecule, like methane, and you know methane's tetrahedral, so you would just know that this was tetrahedral. Yeah. But if you look at it and you go, wow, that looks just like ammonia, only it's got something on the z-axis, which doesn't change its rotational symmetry, doesn't change any reflections, then it's still C3V. Okay. What if this was methanol? Do we have methanol? Come on, people. Just put a hydrogen on here, okay? In your mind, so make this molecule into methanol. It's no longer like ammonia, is it? Because that hydrogen is sticking off axis. That breaks the threefold symmetry. So we had threefold symmetry in ammonia. We had threefold symmetry in this molecule. But if you put a hydrogen on that oxygen, it's no longer threefold symmetric. It doesn't have a C3 axis. So it can't be like ammonia. So then you'd probably have to go through the flow chart and think about its particular point group. Okay. Wow.
That'd be a long break.
1, 2. Okay, I'm going to guess on this one, honestly. I don't know the answer. Okay. All right. You guess tetrahedral? I was going to guess that too. Now people think I'm copying you because you said it first. But look at, it's got a tetrahedral feel to it. Just look at this hydrogen and look at the angles this hydrogen to this hydrogen. Let's look down this one and see threefold symmetry. All right, we have threefold symmetry here.
Yeah.
I'm going to grab this hydrogen here and move it to the front. Threefold symmetry. Okay, I'm going to grab a different one, move it up. Threefold symmetry. I'm going to grab a different one and move it up. Threefold symmetry. So it looks like methane in terms of its threefold symmetry. I'll let you go through the flow chart with that one on your own. Okay. Well, we can do it. We've got 5 minutes. Okay. It does not have multiple C infinities.
Yes.
Does it have 2 or more unique C3s? Yes, it does. C5s. I don't see any fivefold symmetry in here. I see, yeah. So you just kind of got to look around the molecule and see if you see any fivefold things to get a fivefold axis, and I don't see anything that is 1/5 of a turn, so I'll say no to that. C4 axes, I mean, I see 3s everywhere, but I don't see any 4s. I don't see any C4s. This looks like a C2, right? But that's not a C4, so we'll say no. Lots of reflection planes, right? There's one right here, so definitely more than one reflection plane. And does it contain an inversion center? Okay, let's turn this around. No, it doesn't. So let's just look at it at this angle here. Notice these little 3 hydrogens here have nothing to invert into. Once you find something that breaks inversion, it's over. There's no inversion center. So we'll say no. Tetrahedral. Of course, we can really see some cool stuff now with this. So that's pretty fun. Let me hide those, and then let's show some of these. These are the C3 axes, and so it's pretty cool. That's the one I wanted to see. Yeah, isn't that neat? So they put a lot of work into this website, and so get familiar, be able to do the point group of any one of these. They get some pretty crazy ones too. Posner molecule. Yeah. So have fun with it. Okay. All right. Enjoy. Next time we'll see more about the character table.